Welcome back. This is video 2 of a 3-part video series. In this video, we are going to look at one of the first classic example, at least I consider it, the first classic example of an optimization problem. We have our good friend, Farmer Bob, with us. And Farmer Bob has 1,000 yards of fencing, and he wants to enclose or build the largest possible rectangular fenced-in area. The key is largest. When I hear largest, I think I want to find the maximum. And the question is, what are the dimensions of the rectangle that maximizes the area of the rectangular plot? In these problems, I typically like to draw a picture first. So here's my picture. I like to use X for horizontal distances, Y for vertical distances. You don't have to, but that's my preference. And the thing that we want to maximize is the area. And what's the formula for the area of a rectangle? That's right. Area equals X times Y, or in base times height, and in this case, X times Y. The other thing we know is that Farmer Bob has 1,000 yards of fencing. The 1,000 yards of fencing correspond to the perimeter of the rectangle. And one of the things you're going to find in most, if not all, of these optimization problems is a constraint equation. Our constraint is that the perimeter has to be 1,000 yards, and the perimeter of the rectangle that I have drawn to over here on the left side is 2x plus 2y. And what does that mean? Well, that's my P. That's the perimeter, but it has to be equal to 1,000 yards. I'm going to switch colors here. This is the constraint equation for this particular problem. Now, one reason the constraint equation is valuable is if you notice over here, our function that we're trying to maximize has two variables. Well, this is single variable or one variable calculus. So what I'm going to do is solve for y in the constraint equation. And when you go through the algebra, let me use blue. When you go through the algebra, you find that y equals 500 minus x. Then what I'm going to do is I'm going to use this y value to plug into the area function so that I have one variable. And so now what we get is that the area, I'm going to call it a of x, equals x. I'm going to replace y with what it is in terms of x. And so now we see, I like to distribute this x to each piece. Okay? So this is our area function, and remember, we want to maximize the area. And so how does one go about maximizing in calculus or finding a maximum? That's right. We take the derivative, we find the critical numbers, and we identify the endpoints. And because of all we've learned, we know that the maximum or minimum has to occur at either the endpoints or at one of the critical numbers. Note, in this particular example, the smallest x would be 0, which is silly, and the largest x could be is 500. The reason I say 500 is one can imagine rolling the fence one direction 500 yards and immediately rolling it back another 500 yards, kissing the other side of the fence. Okay, so now we're going to take the derivative and find the critical numbers. So a prime of x equals 500 minus 2x. And then we need to solve 500 minus 2x equals 0, which gives us x equals 250. Now what we're going to do is we need to check that in fact this is the maximum. And so when you plug these values back into the original function, the endpoint 0, we get 0. When we plug in 250, well, let's A again. That's 500 times 250 minus 250 squared. I believe this may be wrong, but I think it's right. 62,500. Okay? And when you plug in A of 500, the right-hand endpoint, you get 0. So what is our maximum? Yep. Our maximum occurs when x equals 250, but we haven't answered the question yet. Remember, the question wants to know what are the dimensions of the rectangle that maximize the area. Well, when x is 250, I can go back up. I'm going to sneak through here. I can go back up to my constraint equation and plug in x equals 250, and I get the final answer is the dimensions that maximize the area are x equals 250 yards and y equals 250 yards. Now, just be careful. What we're going to do to you is we're not just going to have any old rectangle. We're going to have a rectangle where we say divided into 3 equal pens. So now, how does that doesn't change the area. That doesn't change the area of the rectangle, but what does it change? That's right. It changes the perimeter. So our new constraint equation would be, we still have 2x, but now it's plus, that's right, 4y. Okay, hope you enjoyed that, and stay tuned for our third video.